We've been working on humanoids for more than a decade at Boston Dynamics, always keeping a close watch on when the missing pieces of technology would fall into place to make it truly commercially viable. The rapid advancements in AI over the past few years are the piece that we needed, and that moment is finally here. Now it's time to officially take Atlas out of the lab. So for the first time ever in public, ladies and gentlemen, please welcome Atlas to the stage.
So as you can see, Atlas really does stand up the way that we show in our videos online. And we get tons of questions about this. Zach, while we have everyone here, do you want to provide a little bit of insight into how we made that decision?
I mean, it's pretty simple. Atlas doesn't have to move like a person does, and we're looking for the most stable, efficient way to get up, and it turns out this is it.
The other question we get all the time is how Atlas is moving. How is Atlas moving today?
So in normal operation, Atlas is fully autonomous on a job site, but today, Sarvesh, one of our FAEs, is piloting Atlas on the stage, giving it really simple instructions like forwards and backwards, just to keep things simple. This is Atlas's first time in public, and as you can see, its walk is pretty natural and pretty smooth. We've partnered with our sister organization, the Robotics and AI Institute, to push the limits on natural walking just for this performance, and I think we've done something really special. We've also been at this robotics thing for a while, and we've learned that there's more to it than just copying nature. We can pick the best parts of what nature has to offer and do better in others. So as you can see, Atlas here has joints that can move 360 degrees. This lets Atlas move even more efficiently than humans, particularly in manufacturing environments where every second counts. We've also designed Atlas's head and face very purposefully. We want folks working with Atlas to know that Atlas is a helpful robot, not a person.
Seeing Atlas live in action for the first time is wildly exciting. But seeing it perform real industrial work is even more compelling. We recently took this robot down to the Hyundai Motor Group Metaplant America to have Atlas test in a real manufacturing facility where we performed autonomous material handling tasks. We proved that humanoids could be viable in a real-world application. And we collected data and learnings that we took back to Boston to make our product even better.
The version of Atlas that you're seeing here is just a research prototype that we've been using for a couple years to understand the system. But we've been hard at work on making the actual product version of Atlas. I can confidently say that this product version of Atlas is the best and actually simplest robot that we have ever built. But rather than just talk about it, why don't we actually show you what it's going to look like? Now, obviously, this is a static display robot. We just couldn't pry the actual production samples out of our engineers' hands at the lab this week. So we're going to be showing you videos of that robot in the coming weeks. This product generation of Atlas surpasses any other enterprise-grade humanoid. This robot has 56 degrees of freedom, mostly with fully rotational joints, and it has human-scale hands with tactile sensing in the fingers and palms for dexterous manipulation. Atlas's 360-degree cameras see in all directions, so it understands when people are approaching, which is part of our holistic safety concept. Atlas is also strong. It can lift up to 110 pounds and reach up to 7.5 feet in the air. Atlas is also water resistant. In real industrial environments, robots need to undergo washdowns, and it can operate at its full capabilities, including strength between -4 and 104 degrees Fahrenheit. It's going to be easy to teach Atlas new tasks. Most can be trained in less than a day. Atlas can perform these tasks at a reliable, consistent pace for about 4 hours using its dual swappable batteries. And when they run low, Atlas navigates back to its charging station and swaps its own batteries, getting right back to work. Finally, Atlas robots share intelligence. Through our Orbit platform, once one Atlas learns a skill, it can be shared with any other Atlas.
These industry-leading specs, along with our industry-leading foundation models, allow Atlas to take on challenging tasks. Tasks that Atlas will do autonomously on its own from day one, assisting people and prioritizing a collaborative, human-centric approach. And as we continue to build out our general-purpose technology, our customers will be able to use our Orbit software to teach Atlas new and specialized skills. Do you want to wrap us up by talking about our production and deployment plans?
Of course. So we've already started production of this new robot at our Boston headquarters, and our entire 2026 supply has already been allocated to Hyundai Motor Group and our new AI partner you'll hear about in a few minutes. We'll add more new customers in 2027. But for now, we're planning additional pilots at Hyundai Motor Group and building a facility that we call the Hyundai Robotics Metaplant Applications Center. This center is the cornerstone of our plan to build the most complete data set in the world to train humanoid skills in manufacturing, creating an engine for deploying tens of thousands of Atlas robots across Hyundai Motor Group facilities worldwide. It's a data factory. Hyundai Motor Group isn't just deploying the Atlas robots either. They are going to build them. Together, we are building a new robotics factory capable of producing 30,000 Atlas robots a year. This is what's truly required to deliver the full promise of humanoids across the industrial, commercial, and home markets.
We are so excited to bring Atlas into the world.
Running. He can do the Macarena. He could do cartwheels. He could dance. I mean, they've made tremendous progress.
There we go.
I mean, for us to turn around, we have to physically turn around. I have to turn around and look the other direction. Atlas just pivots on his core. He can move in ways that we can only dream of. Scott Kindersma is head of robotics research at Boston Dynamics.
So why did you design it that way?
There's a couple advantages of being able to continuously rotate joints. So one is that the robot's not really limited in its range of motion. So it can do things and turn in directions that people just couldn't. Another reason is one of the reliability issues that you often find in robots is that their wires start to break over time. And that's because you have wires that go across all the moving parts. And in the case of Atlas, we don't have any wires that go across those rotating parts anymore.
I think the thing that is most astounding about Atlas is that it seems to actually be learning. Atlas has a brain that is powered by the most powerful NVIDIA chips, and it can learn in different ways. We saw one, they used a teleoperator, and that's somebody who is standing beside Atlas, actually controlling Atlas's arms and hands to pick up things and move them over and over and over again until Atlas can actually do it without the teleoperator moving its hands.
So why does he only have 3 fingers?
Robot hands are an extremely complex engineering problem. Human hands are incredible machines that are very versatile. We can do many, many different manipulation tasks with the same hand. And so when we design hands for Atlas, they don't look exactly like human hands, but they have a lot of the same capabilities. Here you can see that they can switch between different modes. They can act as if they were a hand with these 3 digits, or this digit can swing around and act more like a thumb. And this is really important because it allows the robot to have different shape grasps, to have two-finger opposing grasp to pick up small objects, and then also make its hands very wide in order to pick up large objects.
Can it sense the pressure that's needed or how much it can press on something like this?
So there's tactile sensors, which give it pressure information from each of the fingers. And so you can use that as input to the neural network so that it knows how to do more fine-grained dexterous manipulation tasks. Being able to precisely control not only the shape and the motion, but the force of the grippers is actually an interesting challenge. I think there's still a lot of opportunity to improve teleoperation systems so that we can do even more dexterous manipulation tasks with robots.